All right, welcome everybody to USF Friday Seminar Series. And I'm very glad today to have Dr. Yinhai Wang join us. And, he's a longtime friend of me and of lots of our faculty members as well. And also, he has educated so many students, and then students like Dr. Chongchen is Yinhai's student. So Dr. Wang is a professor in transition engineering at both CE department and also the CSE, Electrical and Computer Engineering of University of Washington. And he's the founding director of the STAR Lab, Smart Transition Application Research Laboratory, and served for quite a long time of the regional UTC, which is called the PAC-Trans, supported by USDOT. And you will listen to Dr. Wang's presentation regarding the traffic in the traffic area. And Dr. Wang is very productive, and he has published many papers, more than 260 papers in the very prestigious translation journals and beyond. And he has received quite a lot of the awards, which I will not elaborate here. And besides all of his accomplishments in translation research, he's also a leader in many of different translation professional organizations. Dr. Wang served as 2018 to 2019 president of the TDNI of SCE, and he's currently serving as the committee chair for Artificial Intelligence and Advanced Computing Applications Committee of TRB. And actually, according to what I know, he actually pushed the establishment of that committee, which is a very timely movement. Dr. Wang also served as the president for CODA, where I had the opportunity to work together with him and I learned a lot from him. And Dr. Wang also served as associate editor for the journals, including Journal Transition Engineering Part A and also Journal Intelligent Transition Systems. So he has a lot of other accomplishments that I cannot elaborate with this limited time, but I just want to say that we're so glad to have you here, and we are very much look forward to your presentation.
Thank you, Yu. Thanks everyone for the invitation. I'm very glad to have this opportunity. Actually, as you mentioned, we're longtime friends. And I also know Sean, Fred Manning very, very well, Kongchen Ching. Fred is actually my mentor. So when I joined the University of Washington, it was because of him. He was the department chair at the moment. Today, the topic I want to share with everyone is called Customized AI and Edge Computing for Safer and Smarter Transportation Infrastructure Systems. So I'm presenting actually on behalf of my research team. We have multiple students involved, and I will acknowledge them at the end. So you people may be familiar with this picture. Actually, I was on your campus 2014 visiting Professor Yu Zhang, and she actually gave me a very nice tour. So I walked around the campus and took several photos, and this is a great memory. I really hoped that I could be there, but actually considering the current pandemic situation, I thought I should minimize the possible interruption with everyone's homestay life. So I decided to do this remotely. But I really like USF's beautiful campus, the great temperature there. So that's a dream place to stay and visit. But I still want to share my beautiful campus. This is the University of Washington campus. We have a lot of different kinds of research work going on, and UW being one of the top three, most funding receivers in the country. So we have very, very active research. In the transportation area, I have my lab. It's called Smart Transportation Applications and Research Lab. We have a lot of data. So you see we have over 20 servers connecting to different agencies. There are even loop detector data only. We receive 50 million lines each day. So we get tons of data accumulated, and we can support a lot of research about big data analytics and artificial intelligence. So we certainly welcome those of you who are interested to, do a PhD study. And I hope when you consider where to go, and UW Starlab is one of your choices. So I want to start by talking about how complicated the transportation system is. So this chart is actually showing the vehicle miles of travel from November, actually, 2019, all the way to like August 2021. You can see that this blue line is the actual vehicle miles of travel that our Starlab's traffic performance score website captured. So that's the true travel using the freeway network in the Seattle area. And the green line is showing, if we consider January 15 through February 15 of 2020 is the baseline, because that's before the pandemic. So how is the current travel compares? You see, actually, we have a big job. The biggest job is actually the weekend after our governor issued the homestay order. And then vehicle miles to travel has been rebounding. So now it's rebounding actually above the 0% line, means it already surpassed the baseline level. So we have just a lot of vehicle travels now. But during 2020, pretty much you see actually the vehicle miles to travel is under the normal level. But we have actually been seeing something very strange. So this is actually the overall, traffic safety situation, right? So you see like these bars are showing the total number of people killed by the roadway traffic accidents. And this black line is showing the rate. It's like a fatality rate per 100 million vehicle miles to travel. So we see this been declining, but in 2020, we saw a 24% increase. And this first half year of 2021, we see another 18.4% increase. What happened? So why we see fewer vehicles on the road and the lower vehicle miles of travel, but with such a significant increase of traffic crashes? So that's clearly a challenge to transportation professionals. Another important thing I want to mention here is the efficiency challenge of our transportation infrastructure system. For example, this is a picture from the Los Angeles port. The number of cargo vessels are waiting, try to deliver the containers. And you see the port is already busy. And we see a big interruption of our supply chain, not to say the 44% increase of e-commerce last year. So there's just a lot of things changing, a lot of things going on. And clearly, we're facing these challenges. And as transportation professionals, we need to find solutions. Maybe the first thing we need to answer is why these things happened. And then what to do, right? So how do we, find the reasons and provide a solution to address these challenges? Through our study, we all know that we have a lot of transportation data. Historically, we have these, classical traffic sensors, like acoustic sensor. This is radar sensor and infrared sensor loop. We use a lot of loop detector data, video, and the combined sensor. But recently, we have more data sources, right? Like the Internet of Things bringing a lot of sensors to your daily use life, like issues, data used items, your phone, social media accounts, your search, connected automated vehicle, even the garbage collection bin, they may have a sensor reading the Bluetooth signal. So we got all these data, and combining these data, we form a transportation big data stream. And this is something new, like in the past of research, we're constrained to very small amount of data. But now we do have a lot of data. And these data sets are actually very valuable assets for transportation researchers. But we're facing all these data. And most of us, at least from the classical transportation engineering curriculum, we do not train students, how to use like a database tools, how to design database to store your data more effectively. So we definitely face, some kind of challenges and puzzles. How do we make a good use of these data? What are the right approach? So this is certainly a challenge, but also the opportunity. It gave us the chance to reconsider how do we do transportation research? How can we develop new methods to make it more effective in addressing our challenges? So I want to start to say like the classical transportation system and the methodology provides, like a limited amount of data, and therefore the methodology is pretty much based on the mathematical assumptions and then like a closed form equations. A good example is actually the traffic flow theory developed by Bruce Greenshields. So we all know like a fundamental traffic flow theory that he developed. But at that moment in the 1930s, the data he collected was using camera, and he stands by the road and take photos. And when he took the photo, he actually have a clock there, so he sees also the time and see the vehicle position, also the time differences, and try to calculate travel time, etc. So this is actually one of the earliest paper about traffic flow theory. So this is the one published in the proceedings of the 13th annual meeting of Highway Research Board, which is the former format of the Transportation Research Board. So this like a flow speed diagram is actually very classical traffic flow theory. Maybe you all remember, so when we look at this flow chart, at the place that the flow near to break down, there's a lot of uncertainties. So you see actually more dots, placed randomly, and this shows the value change a lot. But is this really because of this or because of the way we collect data and do the analysis? Let me show you this right side chart. This one you see, this is actually the trajectories of the vehicle. Let's consider this is a roadway segment where you have a sensor like at upstream and downstream. If there is a particular incident that occurred, for example here, and then vehicle will slow down and gradually queue up. So it will take much longer time to really detect it. Let's say this vehicle did not capture it, and all the way vehicle queues up until the upstream sensor detects the slow movement, and then you consider, oh, there may be something happened. But the moment you captured the volume and possibly the speed is not exactly corresponding to when the incident occurred. So I consider this is because of the data constraint, and therefore we have been getting this very important fundamental traffic flow theory, which may have a problem. Now we have a lot of new sources of data. For example, the outsourced data, like if you use Google Map or you use Waze, you are contributing data to the app owners. Let's say you may get your trajectory data, right? If we get every vehicle's trajectory data, we know exactly when the incident occurred and when the vehicle slowed down, queued up to the upstream sensor location, how long it takes. And if you look at the loop sensor data and finding the right pair of speed and volume, that may really significantly reduce the uncertainty at the breakpoint. So that's my guess. I think this may be also an interesting problem to investigate. I just want to use this example to show we do need new traffic flow theory and other transportation theories. We have a lot of data, and these data will be supporting that kind of effort. So over the past years, with the increasing amount of data, what we have been doing is placing the data into a platform. This is actually a research work example from my lab. We developed a system called DriveNet, and it really oversees different kinds of data. We can do data fusion, but the main purpose has been visualizing the data. So we do little about exactly what caused different kinds of problems. And this is still something, with a lot of room for transportation researchers to invest their time and energy in. So over the past several years, the hottest term may be AI. And if you look at why AI suddenly become very, very popular, actually this important, robot versus human game played a huge role. Maybe you guys, if you know the Go game, you may have already heard about this. In 2017, AlphaGo shocked all the Go players in the world by winning this best human player called Jie by beating him 3-0. And he felt desperate because he's the best player. He worked really hard. The first game was close. The second, the third game, he just had no chance to win. So this demonstrated the power of AI, because AlphaGo is purely based on AI, and they learn from all the previous games the human players played. But AlphaGo soon beat by AlphaGo 0. 0 means they learn nothing from human. They only learn from itself. Like this particular software just play with itself. And after only 40 days, AlphaGo 0 beat AlphaGo Master, so the software that beat the best human player, Jie by 89-11. And this was only in 40 days. So this machine is fully trained, and human just has no chance to beat him. So AI is certainly great, but it doesn't mean AI is just a superpower, it will be good at everything, but it can certainly beat human in a lot of different things. And there are a lot of research about which particular field AI may be used and gain people's trust first. So this is actually from the Stanford research report, 100-year study on AI. So it said transportation is likely to be one of the first domains in which the general public will be asked to trust the reliability and the safety of an AI system for a critical task. We all know there are a lot of companies testing like autonomous vehicles, Waymo, Uber, etc. And there's also a lot of interest to see how we can solve the first and last mile problem by doing, for example, the drone deliveries. So these will all be running AI algorithms. And this is so critical. The improvement has been so big over the past years. So we see there are more and more places actually testing level 4 autonomous vehicles. So certainly AI will have a role to play, and maybe even a very, very significant role to play in transportation research and practice. But we cannot just directly grab the AI approach and use this in the transportation system. You can still find the benefit, but it may not be very effective or efficient. Considering that AI has unlimited number of parameters that you can use, you could put just more layers and get more parameters involved, and then you can see more accurate result. But if you are familiar with modeling, the more parameters you throw into the model, you will improve the R-square or other metric that you use. But if you adjust it by the number of parameters you use, it may not be actually a good approach. But AI just don't look at that. But still, in transportation system, we have a lot of our own features. for example, a transportation network, you only see vehicles moving from upstream to downstream. Even there are two parallel roads, they have no interaction until you see the crossing roads linking the two together, right? So these are the kind of features, if we apply properly, we can significantly reduce the amount of parameters involved, and therefore we can make our model to converge quicker and saving a lot of computing resources. So I will not spend too much time on more examples, so because I will emphasize more on edge computing and edge AI today. So if you're interested, so here's an example that this research done in my lab, led by Dr. Ruiming Ke, who is now assistant professor at UT El Paso. So this paper is just so a great example how you could customize the conventional AI approach, make them fit in transportation system well. So today I want to show you an example for edge computing, and also how can we use the technologies to address our challenges. So if you look at the traffic crash numbers in 2020 and the number of people killed, that's certainly a huge alarm that we need to pay attention and see how we could improve our safety situation. Connected vehicle has been a keyword for many, many years that people use to see how this technology may help to reduce the number of crashes. According to the US DOT, and this technology has the potential to reduce traffic delay by 33% and possibly eliminate or mitigate the severity of up to 80% of the crashes, with non-impaired, like a driver's influence. So it can also save energy. So let's see how this particular system works and what kind of technologies that we need to make this work at the level that's desired by the transportation professionals. This is actually a figure showing a typical connected vehicle system. So we designed this really well, but I see actually there's a lot of problem to implement this. Let's say if there's a crash occurred here, and this crash will be reported by some vehicle to the roadside unit, and the roadside unit will pass the information to like a traffic information or control center, and this center will be informing the right places so the drivers can hear about this and take some actions to avoid secondary accidents or choose another route to mitigate the congestion at the accident spot. However, if we look at how the flow is going to work, so this is actually the kind of traffic sensors collecting data to support traffic signal control. And these sensors manufacture has nothing to do with the roadside unit. So all they do is provide the information needed by the traffic controller. And similarly, traffic controller has nothing to do with this roadside unit. All it does is process the sensor data and decide when to give the green signal to which particular movement. So therefore, all this information get to the traffic control center, and the control center staff need to make a decision. Is there an event I should inform road users using the connected vehicles? Where to inform, which particular roadside unit I should issue the information sharing. So these people must know the whole system really well and make a decision. But unfortunately, most of these people were not trained with any knowledge about a connected vehicle, and therefore what they can do is limited. And you can consider if you make everything to be supporting the connected vehicles, all these things need to be upgraded. And the investment is not a small number. Not to say, in our roadway network, we do have some traffic sensor data. In some places, it's even redundant. Let's say in this example, you have a lot of cameras installed, but each data stream collected by different sensing technologies will go to their own system and data format. And these data collected in different locations And we are lack of an approach to integrate all these data together. So when these data get to the end user, they just feel it's so hard for them to integrate and make good use. So in my conversation with Washington State DOT, they have a strong desire to get a training about how we can integrate the data we already have, but in different formats, stored in different systems. So for people without database knowledge, it's really hard for them to do anything. But in most of the places, we have major traffic information missing. For example, the weather information. So this is the weather information station. Each station will cost like $70,000 to $100,000. And in the whole Washington state, there's only less than 200 such stations. So you can imagine it will not be sufficient to provide the weather information to the entire roadway network in the state. Very, very few places have this visibility sensor, like measuring how long a driver can see. So this is a $20,000 or more each, and therefore we also miss a lot of critical information. So if we want to make connected vehicle work, right? So you need to disseminate the right information, identify the events, and inform the users about this particular event. But we have the missing information. We have the challenges of combining the existing data together. So this has been a challenge at TMC. And this is also why you have seen like a lot of roadside units deployed through the US DOT's pilot projects. But I heard 0 success stories. No success story ever reported. And I just consider if there's no proof of the value, should we continue to make the investment? So in my opinion, we need a kind of magic device here. If this device is there, being able to sense, fuse all the sensor data, make the right decision, and inform the local users about what happened, I think that's desire. That's going to be saving a lot of money and also saving a lot of trouble for the TMC staff. So this kind of magic device that we have been working on over the past 7 years is called mobile unit for sensing traffic. So this is also the edge device that I will show you today. Some of the algorithms we developed using customized AI and edge computing technology try to enable a lot of functions to directly serve the practical needs of our transportation community. So this particular device is able to sense roadway conditions, sense traffic, sense temperature and environmental situation. It has a lot of technology integrated, like the computer vision, MAC address sensing. So MAC stands for Media Access Control Address. We use edge computing, customized AI to support various kinds of functions. And we also have the V2X function. Now currently we build this up with the Wi-Fi, but we can easily switch to like CV2X. So this, by using this technology, we'll be able to collect data and fuse data and do the analysis, make a decision, all in this edge device. So everything will be easy, and the combined information sent to one single data system supporting the center staff to make the right decision. So this is actually the device we have developed. So before we actually talk about how we do different kind of functions, let's briefly introduce what is edge computing. So the edge computing is relatively a new world, and the edge AI is even newer. So computational processing of sensor data away from centralized nodes and close to the local edge of the network. So this is the definition of the edge computing. The key idea is, instead of relying on the cloud or server to do the computing, let's do the computing on site. So the benefit for doing this is you process everything locally. You do not require high bandwidth communication system support. And also for agencies with a lot of privacy concerns, this edge computing handle everything locally and only send the information needed, for example, speed, volume, travel time, and this will minimize the concern of people. So this edge computing, I do see it has a lot of potential. So certainly a lot of benefit for using the technology. And the key thing, as I mentioned, it does not really require high bandwidth communication system. It can be protecting privacy better. And this is also something you could, just stand alone without, paying extra money for server or cloud. So there are also challenges. So the edge computing is normally relying on a very small device. For example, a Raspberry Pi, Jetson, like a NVIDIA Jetson. So these are all devices with very limited computing power. You have to really design your approach well to make it work. So the computing task and the loads must be carefully balanced and optimized between edge device and the cloud. Sometimes you have much heavier work than the edge device could do. Let's say we did like a parking detection system using edge computing. We have certain work done on site, use the edge device, and also send pictures back to the server computing the rest of the work, like a matching, is this the vehicle parked here some time ago? So in that way, you can continue to time that particular vehicle that occupied the parking slot. So system integration and the reliability of hardware, software, and data communications, this is much more important because the resources are so limited, you have to make a great use of every piece, software design, hardware configuration, etc. This is my firm belief, and there's also a lot of articles talking about transportation takes a leading edge in edge computing. So I can foresee this is another very hot and important research area. So AI is certainly already very hot. I think the next one will be edge computing. If you guys want to choose a topic for your research, I think this could be a great PhD research topic. Let me continue to show how we build different kind of algorithms to address the challenges. So this is actually one example that we apply to a research project funded by Norwegian Public Road Administration. So in Norway, there are a lot of fisheries, and their fisheries are mostly inside the Arctic Circle. So that means in the summer they have 24 hours light, and in the winter they have 24 hours darkness. So they have relied on this corridor. It's called the E8 corridor to transport salmon from the fisheries all the way across the border with Finland and load down the airplane to fly to Asian countries. So certainly the reliability of this particular corridor is very important because Norway has very limited amount of people, and they have a very, very long shoreline. And for freight vehicles using this corridor, if there's anything occurred, they want to know, but they cannot patrol this corridor very frequently. So that's why they want to install 9 of our sensors along the corridor and try to detect which particular segment may have a travel reliability issue. And therefore, they can assign the incident response truck to there to fix the problem. So the objective of this research, certainly we want to detect incidents, and if there's anything happened, we need to inform the incident response crew to address the challenge. We need to measure travel time and reliability between sensors. We also need to know road surface condition because the travel time expectation for a dry pavement versus snow covered, ice covered will be very different. So we need to know what is the situation, and we need to detect the vehicle so we can detect travel time and also measure the temperature and humidity of that area so we can have a right judgment of incidents or like warning events that we should issue. So this technology is mentioned to you. We have built the V2X communication road surface monitoring vehicle counting. This all use the edge AI approach. So we can estimate travel time and detect the temperature, humidity. So this will be helpful for us to judge if the road surface is wet pavement or is covered by black ice. We can also use the sensor to detect the visibility, so how long a driver can see. So here is actually some details of the methodologies that we have used. So the key thing is, because the edge computing device is relatively slow, it cannot compute, a video image, just instantly. It takes about 2 seconds in our current algorithm to finish. But how do we ensure, this is the moment you trigger your edge AI approach? And if you triggered, how could you ensure there's no vehicle missed and no vehicle will be double counted? So we have to build actually 2 different threads. One thread is actually we decide, is there any vehicle here? If there are, so we can trigger the AI approach. And if we trigger the AI approach, we need to track, that vehicle entered the scene, like the first one entered. And with this vehicle still in the scene, we don't have to trigger the second, image to process. So once this vehicle out of the scene, we can trigger the second image. So in that way, we'll not double count vehicles. And certainly, vehicle will take more than 2 seconds, so we will not miss vehicles either. So here are some examples that we have done. Road surface detection is a separate approach. So here we use, like a roadway mask. We generate, where is the road surface. So in this way, you set up the sensor, and the sensor can process the video images triggered by actually it's conventional method, not the AI approach. Like the conventional method take very, very minor computing load. So that's something we keep running. Once AI approach is triggered, so we detect, for example, what's the surface of the roadway. But before we can deploy the sensor, as you know, we need to collect enough data to train our model, right? So this is actually the data we collected using the surveillance video cameras that our lab has, the access with. So we have access to about 1,500 surveillance video cameras deployed, through the Washington state. So we collect, images. This is like snow and the water coverage, right? So this is snow, and this is icy, and so this is the regular pavement. So we train the model to recognize, hey, this is actually the roadway covered by ice. So we have to get volunteers to label the video images, and then combining the environmental sensing data and the image and try to make a judgment. So this is a train in like the local data, right? So through our training, and then we test, we have to do a transfer learning. So before we deploy this to like Norway. So this is actually the kind of result we tested. So the methodology, we have applied multiple different kind of methods and see which one works the best. And the results is, for the dry pavement, we get 97.5% accurate. For the rainy situation, we got 85%. But in the rainy situation, what it confused the most is with the partial snow situation with 3.2%. So this is still a very, very good result. Using the conventional video image processing method, you normally cannot accomplish this level of accuracy. So for vehicle detection, as I mentioned, edge computing, a biggest challenge is how can you allocate the limited computing resources for different tasks. We have multiple threads running at the same time. If you want to detect vehicle and recognize what kind of vehicle this is, it takes quite some computing work. So what we do is actually we detect the moving blobs first, and then extract this particular blob and apply the AI to go deep to see exactly what kind of vehicle this is. So in that way, we can detect how many vehicles goes by this particular section of road, and also what kind of vehicle. So we use actually deep neural network classifier, so combining with the classical method. So that's kind of way of customizing the AI and make a good use of the edge device computing power. So for the traffic, the data like vehicles we detected, we also need to be classifying what kind of vehicle they are. So this is actually our result. So we actually use the mobile net data to train our model. And we also apply for transfer learning. So this is actually the result we got. For car, we detect this at 91% accuracy. For truck, it's 87%. So certainly there are different kind of vehicles. Depending on your training data sets quality, this could be different. But this mobile net data is widely available to use. And so this is something we just directly grab this data source and applied. So that's about the kind of research work we have been doing. There are a lot of different things that we tried, different AI approaches, and which one may be easily customized, which one may not. So we actually have a lot of papers published. If you guys are interested to know more details about the specific method, you can go to my Google Scholar website. You can see all those papers we published. So I just want to share another thing. It's also good for edge computing, which is the curb space management. It's another field with a huge demand. Actually, we were selected to do a demonstration for the Southwest by Southwest event. It's the musical event to be hosted in, I think, Austin, Texas. But this was canceled due to the pandemic. We were supposed to be demonstrating our edge computing method using for curb space management. But luckily, we actually got the chance to be testing the approach in the city of Bellevue's curb management pilot project. So the city invited us and also 7 other companies, all doing their device, installed in the location and try to collect data to do the analysis. So to my surprise, actually, our labs product, we end up to be the #1 product in accuracy and beating all the competing companies. But it's kind of interesting to see, if you look at this accuracy, that's not very, very high, right? So some places only like 69%. There's still a lot of ways to improve. And currently, we have been working on a 3D traffic sensing reconstruction approach. So this is trying to localize the particular vehicle using the 3D model. And this way, I think autonomous vehicle, if they want to locate itself, now they have to do 3D mapping. And 3D mapping take a lot of computations and normally consume a lot of energy. It's not good to do. So if we could use the roadside device, try to solve this problem, I think that's a lot better. So here is actually our approach. This is the methodology we use. We have been continuously working on the methodology to make improvements. I will not go through all the details. I think I will share this PowerPoint file. Later you guys can go through and raise questions if you have. So here, maybe I can show you a demo of how this particular thing works, a very short video. So this is actually collected from the video, like our sensor installed around the city of Bellevue. That's something we'll be continuously working to improve the accuracy of our model. So given the time constraint, I want to stop here. But before I end my presentation, I would like to appreciate the funding sponsors who supported our research. And in particular, I want to appreciate my PhD students, Ruiming Ke, Chenxi Liu, and Zhiyong Cui, who actually are the driving force for this research. So I just want to save some time for questions. So I will stop here. Any questions, please bring them up.
Great. Thank you so much. Yeah, so for all the audience, you're more than welcome to unmute yourself and raise your question. And also for the students in the classroom, if you have question, you can either let Zhao Hui to type in the meeting chat, or you can also speak up.
Maybe I can start with a question.
Yeah. Go ahead.
If no one has. So, Dr. Wang, it's very nice presentation. I enjoyed it very much. Great to see technology development from your office which is really, challenging and successful as a university lab. So you mentioned about the edge computing, and there is one thing that is a kind of challenge is about balancing the computational tasks between edge edge nodes and the cloud. So can you share some general principles about how to divide and optimize the computational task distribution over the edge computing structure in the context of transportation applications? Thank you.
Sure. Thank you, Xiaopeng. That's a very nice question. So this is a kind of important because when we were working with Sound Transit for a parking detection project, so we have our sensors installed in the parking garage. And for any kind of existing sensors, for example, magnetic sensor or like ultrasonic sensor that's widely used, they can only detect if this particular slot is occupied or not. They do not know if it is occupied by the same vehicle. Let's say this vehicle is occupied, maybe back out of the sensor and go back. It's still the same vehicle, and you cannot park there for like over 24 hours. But if this vehicle just move out and in, it will fake, the other kind of sensor. So we have, our master sensors, the earlier version deployed, and we can know if this slot is occupied. So if there's any movement, let's say this vehicle moved out, another vehicle moved in, and we detect the event and the trigger sending of the picture to the server at the Starlab. And the Starlab server will do the comparison of this current picture with the previous, parked vehicle's picture to see if this is the same vehicle. But if you do this kind of vehicle re-identification on the edge device, it will take a lot of computation power, given each sensor is monitoring, 8 to 10, different parking stalls. It's going to be impossible for the edge to do this. But if you send all the pictures, you will consume a lot of communication bandwidth, right? So, and that's also generate a high cost because we were using a data package from the cell phone company. We don't want to, exhaust the data package we purchased. So we want to minimize that. So this is just an example. Some necessary amount of work to be done on site and leaving a more challenging task to the cloud. But if the edge computing device is improving with the computing power, everything could be done locally, that's even better. But recently, there's also, they call it Federated Learning. It's like combining all the edge devices. They each learn something, and then they share what they learned to the server, and the server can combine every sensor's local learning results and disseminate, the updated parameters to improve the performance of all the edge devices. So I think this is another example. It could be used in transportation for a better, sensing or smart infrastructure applications.
Well, thank you very much. Yeah, and I think this is a very intriguing problem, and I can see also, I'm just thinking for some localized problems like detecting the parking spots, you could use the edge computing if the computational power is sufficient. And for some more of a global level tasks like coordinated control of the transportation networks, or like a green wave, or like these actions that you need to coordinate the information from different devices, different places. Maybe there would be some opportunities for aggregating, processing all the information from different edge nodes to the cloud. Yeah, just some thoughts, and I really enjoyed your talk. Thank you.
Thank you, Sean. I think certainly there are a lot of potential applications of the edge computing methods. So simply the master sensor that I just briefly introduced, that's developed by the Star Lab. We have been using this for monitoring the roadways, right? So just like I mentioned, the application in Norway. Another application we're doing is I also mentioned the edge computing for curb space management. We have several sensors designed and developed to do, you guys may know the SPAD challenge, right? Like signal, facing, and the timing. That challenge raised by, I think, Ashton. The goal was to have 20 intersections in each state to have the connected vehicle device at intersections. So we were targeting pedestrians. So those systems could be installed at the intersection. And we have also an app developed. People can use the app to request the traffic signal. If you want to cross the street, you can request that. And you can also see how many seconds left there. We're adding more functions to our sensors. We can also track pedestrian when the pedestrian is walking, crossing the street. Normally, pedestrian has no signal extension, right? Vehicles has. But if pedestrian could be detected, maybe a senior person is walking, you just extend the green signal by several seconds and try to make sure that person finish walking. Now using this kind of system, it is possible. So I just see a lot of things we could do. Maybe a lot of local, like transportation agencies who do not have a lot of money. If you want them to be applying connected vehicle technology to improve their safety or efficiency, they may not have the money, maybe $1 million or more. If they have just money to buy a sensor, they could do that, right? Or deploy a sensor and, customized algorithm implementing the software to do what they want to do, like counting pedestrians. These are terrific applications of edge computing technologies. It doesn't even require you have a fiber connected there, or you have a fast speed, communication network.
Thanks.
Thank you. Thank you, Xiao, for the question, and thank Dr. Wang for the answer. And we do have a question from audience. The cutter. Zhao Hui, could you please ask the audience to speak out to the question?
Sure, we got one question from our audience. I will let her speak up now.
Okay, thank you so much. Thank you, your next presentation.
There's some echo.
This echo.
Maybe the local person can repeat the question to me.
Okay. And I just want to ask a question about the accident date. Do you have any form based on the map to add all the accident date on the map? And because you know that and from your presentation, I saw that there have increase in the accident rates and during last year or this year. And did you do some research or just the model estimation on the temporary increase or not? Thank you so much.
You mean the number of crashes and the fatalities increased in 2020?
Yes.
I think certainly Professor Mannering is the top expert on this. So I did do my PhD in traffic accidents analysis. So there a huge increase. I'd say 24% in 2020 and 18.4% in the first half year of 2021. So these are based on the data observed. So exactly why is this? I think part of the reason is fewer vehicles on the road and people tend to drive faster. Another reason could be because people don't want to use transit and they consider transit will have too many interactions with other people. They want to drive, but not everyone has been driving, right? So a lot of newer or less experienced drivers on the road, that could be another reason. So I think we need to use AI approach, try to identify more. And Professor Manning and we try to collaborate on some proposal. We're waiting for the result. So hopefully we can win that and we can make some investigation on that. This particular technology I presented actually has the potential to really cut that down. Let's say you have a roadway with a huge curve, with a lot of departure accidents, and that may be because the road surface is too slippery, right? But how would people know that? If you detect, oh, there's the black ice there, and you just broadcast through variable message sign or using connected vehicle message to people who has the app and they receive that and they drive there with caution, or the incident management crew come there, put some sand, put de-icing chemicals, that will solve the problem. I guess Professor Manning can give you a much better answer about the increase of the crashes.
And yes, and because I'm also a student of Dr. Manning, and from his ever project about the Washington State, he just make a statistic about all the the interstate highway and the pavement quality, pavement condition. But I found that there's some the data error in his in the original date. So just I have wondering that how you just your current the data set you used and you are using, and just you put more and from the data, what kind of UV and the data, just the data accuracy perhaps is yeah.
You mean date?
Yeah, data date.
Okay, so I think the original record, because I do have the original record, like for crashes, they're like exactly when this accident happened, what kind of situation. But through my discussion with Professor Mannering, we know the existing methodology normally need to be bundle all these things together. You cannot really put the variable inside a model. Let's say this accident occurred, it was raining, but you can only do this section of road. You have X accidents, and there's Y days of rain in this area. So that kind of variable. But maybe there's 3 accidents all happen when there's only 1 rain each year, 1 day rains that each year, but it all happened in that day. But in this current modeling approach, you just cannot reflect that. So that's another good reason, look into the AI approach and try to do something different.
Okay, thank you. Your answer.
Yeah, Dr. Wang would be more than happy to discuss afterwards if you still have questions on this crash data. And let's see if other audience have questions towards Dr. Wang. Yeah, I saw somebody raise a hand. Please go ahead.
Hi, Dr. Wang. Thank you for your nice presentation. I just got one question regarding one of the slides. You showed the classification results for the load condition. I think like for the rainy low surface with water. I showed about 86% something. I'm just.
So you want to see the result? Okay.
Yeah, I think you showed one slide showing the classification results, and for
this one.
Yeah, 85% rainy day. I guess like about 7.6% of the raining surface were misclassified into a dry condition.
Yeah. This is like sometimes the dark pavement with light rain on top of it, and this is the very clean pavement. The model is confused for 7.6% of the cases.
So here you use a random forest classifier. I'm just curious, if you combine this information with the weather station data, would that improve the prediction?
If weather data is available, and certainly it's great to use it. So the great thing is we have our own sensor. We sense the humidity and the temperature all locally, and we just integrate this directly together. As you see, actually, you probably have the experience, when you're walking in this side of the road, it's raining. That side is not raining, right? So
okay.
Yeah, and in the whole Washington state, there's only less than 200 weather stations collect data for the roads. So you see this particular method, this is without combining the temperature data we collect. So after we collect that, this is going to be even more accurate. Yeah, so the rainy situation, the dry situation, confused by 7.6%. There's also partial snow and snow. Exactly, how do you define that? You have to find a point. I say this is partial snow, this is snow, right? So that's also have some kind of 4.6% error.
Okay, great. Oh, thank you.
Thank you.
All right. Yes, shall we?
Oh yeah, I have a quick question. So yes, Dr. Wang, it's very impressed the presentation, and I have a quick question. So based on my understanding, I think for the edge computing, it cares more about the performance of some local area, and for the cloud computing, it's more about the overall system performance. So I may want to ask you about your insights, how to balance the edge computing and the cloud computing, since one is about some local performance and one is overall performance.
Yeah, so certainly you are right. For the cloud computing, if you get data from all the data stations over the network, you could oversee what's going on network-wise. But this will need very strong support from the communication perspective. And this particular city or like a region must have a lot of money invested in these things. And you have to pay a lot of money for cloud. Even I'm a fan of cloud computing, I'm still doing quite a lot of work using my server because university is operated by research funding. You may have a lot of money this year and you have no money next year. But the cloud computing, you have to pay, every year, even every month, right? But if you have money, you buy a very good server, and you can all configure the server somehow serve like a role of like a cloud computing device. So that will work fairly well. But for the current situation, it's almost impossible for any city or any region to deploy their overall roadway system with the desired coverage of sensors. They may always prioritize the locations that badly need some kind of sensing technology to collect data to reduce the problem. It could be crashes, it could be congestion. And the edge computing could serve this role really well. You could just put a sensor there, collect the local situation, and issue warnings as necessary. If you need a center staff to decide something, or the center staff needs something from the edge sensor, you could just collect that data, fetch the data from the edge device. You can still make a decision. So I think if we expect suddenly, we have everything to cover our entire system, that's not possible. At least you can see we always lack of money for doing even maintain the situation of the current infrastructure system. So having small amount of money make a nice movement, right? By addressing the most critical problems on the network, that's a more practical approach. So that's why I consider, at least in the current situation, maybe the edge sensor, edge computing could fit in transportation system better.
Okay, I see. So you mean that in this kind of early stage with the financial concern, the edge computing is the best solution. But if we got enough money, the cloud computing will be the final answer for this question.
This is part of the main reason is this. Another reason is for transportation applications, you want a fast response from the roadside device, right? If you can respond from the edge directly and save all the trouble going back to the server and do the computing and coming back. So the I think the delay will be much shorter to handle things in the edge. So even you have money to do everything, I think still certain amount of work need to be done at the edge side.
Okay, thank you.
Thank you.
Yinhai, I mean, I'm very impressed to see that when you compete with other industry companies, actually your device and your algorithms actually performed better. And you also showed kind of a pole with so many different cameras and sensors, and we hope that will not happen in the future. So I was wondering for how's the compatibility of all different products in terms of edge computing and also transmitting the information to the cloud for more kind of system-wired management.
So the current problem with our transportation society is we have all kinds of devices like a small silo. So all devices work on their own way and producing their own data, and they don't crosstalk to each other. And this leaves a huge problem at the end users, let's say the traffic control center staff, because they cannot just integrate the data, make a good use of that. Because the sensors may measuring data at a different resolution level, different location, right? So you need to have very high data management skills to integrate the data and make good use of that. But if you do this edge computing, like the example I presented today, you could do the desired integration locally. It's much easier because it's all measured in the same place. You know exactly where the data is from, what kind of measurement interval you want to set up. So that's certainly much better. It saves all the energies at in the end user side, and this will make the sensor more effective and more useful. Because the current situation is we don't have a lot of data, but at some place we have huge amount of data, and this data is even redundant. But each data may not tell us the complete story, but we do not know how to integrate all the data to tell us the story continuously, right? So I see we need to jump out of this comfortable zone that we have been doing for years, right? Just doing this, as we did before. We need to be switching to a new style of thinking, and also moving to the new kinds of methods and the theory, try to make a big move, a big improvement of our research and the practice. So I would say this is there, and it's certainly very possible for us to do. We just need everyone to set up the mind right and start to work on these new approaches and new products.
Any other questions from the classroom and also from our online audience? All right. I think you can easily find Dr. Wang's email address, and if you have more questions regarding his presentation and also regarding the publication that he mentioned in the presentation, you can contact him directly. And by saying that, this is the end of our seminar, and I want to thank Dr. Wang again for his inspiring and wonderful presentation. Thank you so much for talking in our seminar.
Thank you, Yu. Thanks everyone for joining this talk. I appreciate that. Fred, great to see you.
Great to see you again.
And thank the audience for participating. So I'll see you next week.
Okay, thanks a lot.
Thanks everyone. Have a nice weekend.
Thank you.
Great to see you.
Bye.
Bye-bye.
Bye.